Hello and welcome to the Slumber Lab. I'm so glad you're here tonight. Whether you're already settled under soft blankets, letting your thoughts drift toward the edge of sleep, or simply allowing your mind to wander through the quiet corridors of curiosity, this space is made for you. Tonight, we begin a gentle journey into one of the most profound questions in all of physics. A question so fundamental that it touches the very fabric of reality itself. Could the speed of light, that cosmic constant we've relied upon for over a century, actually be changing over time? But we won't rush toward answers. We'll take our time, like starlight crossing the universe, patient and steady. Before we drift deeper into this mystery, I'd be grateful if you took a moment to like this video if you find yourself settling into the rhythm of wonder, and perhaps subscribe if you'd like more of these quiet explorations into the cosmos. It helps other curious minds find their way here, one peaceful listener at a time. Now, let your breathing slow. Feel the weight of your body. Because tonight we're going to question something so basic, so foundational, that most of us have never even thought to doubt it. The speed of light. That unwavering constant, that cosmic speed limit. What if it isn't quite as constant as we thought? Picture this. You're lying beneath a canopy of stars, each one a distant sun, sending its light across impossible distances to reach your eyes. That light has been traveling for years, decades, sometimes millions of years to arrive at this moment. And every photon, every particle of light has supposedly been moving at exactly the same speed. 299,792,458 meters per second. Never faster, never slower. Always precise. This is what we call the speed of light in a vacuum, represented by that elegant little letter C in Einstein's famous equation. It's been the cornerstone of modern physics for more than 100 years. The unshakable foundation upon which we've built our understanding of space, time, energy, and matter. But what if that foundation isn't quite as solid as we thought? What if, buried in the deepest observations of distant galaxies and ancient light, there are whispers of something different, hints that this supposedly constant speed might actually be drifting, changing, evolving across the vast spans of cosmic time? Tonight, we'll explore this possibility together. Not with urgency or alarm, but with the gentle curiosity of minds at rest. We'll journey through the evidence, the theories, the implications. We'll meet the scientists who dare to question what seems unquestionable, and we'll discover what it might mean for our understanding of everything if the speed of light is not the cosmic constant we believed it to be. The idea itself sounds almost heretical, doesn't it? Like suggesting that mathematics might be wrong, or that gravity might sometimes forget to pull. The speed of light has been so thoroughly tested, so precisely measured, that questioning it feels like questioning reality itself. And yet, science progresses by questioning the unquestionable, by looking more carefully at what we thought we knew, by asking, with quiet persistence, but what if? So let's begin where all good stories begin, with a moment of wonder. Imagine you're holding a flashlight. You point it forward and press the button. Light streams out, racing away from you at that familiar speed. Now imagine you're on a train, moving forward, and you shine that same flashlight in the direction the train is traveling. Common sense might suggest the light should move faster. The speed of the train plus the speed of light. But it doesn't. The light still moves at exactly the same speed, regardless of how fast you're moving. This strange behavior is what led Einstein to his theory of special relativity. Light, he realized, doesn't follow the same rules as everything else. It moves at its own pace, indifferent to the motion of its source. This cosmic speed limit became one of the most fundamental constants in all of physics. But constants, even cosmic ones, live in a universe that's far from constant. everything around us changes. Stars are born and die. Galaxies drift apart. The universe itself expands. Even the most basic properties of space and time can bend and warp under extreme conditions. So why should the speed of light be any different? Why should this one quantity remain perfectly unchanged, while everything else in the cosmos evolves and transforms? The first whispers of doubt came from an unexpected place, not from laboratories or particle accelerators, but from the deepest reaches of space, from light that had been traveling since the universe was young. When astronomers look at distant galaxies, they're not just seeing across space, they're seeing across time. The light from these ancient sources began its journey billions of years ago, when the universe was smaller, denser, younger. If the speed of light has changed over cosmic time, then this ancient light might carry subtle signatures of that change. One of the first scientists to seriously consider this possibility was João Magalhães, a cosmologist who dared to ask whether the fundamental constants of physics might not be quite so constant after all. In the late 1990s, he and his colleague Andreas Albrecht proposed something radical. What if, in the very early universe, light moved much faster than it does today? This wasn't just idle speculation. They were trying to solve one of cosmology's most puzzling problems, known as the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see that it has almost exactly the same temperature in all directions. But according to standard physics, regions on opposite sides of the sky should never have been in contact with each other. They should never have had time to reach the same temperature. Unless, Magalhães and Albrecht suggested, light moved much faster in the early universe, fast enough to allow these distant regions to communicate, to reach thermal equilibrium, before slowing down to its current speed. The idea was elegant, controversial, and difficult to test. How do you measure the speed of light in a universe that existed billions of years before any measuring devices? How do you peer into the cosmic past and check whether photons were racing faster then than they do now? The answer, it turns out, lies in the light itself, in the subtle fingerprints that changing physical constants might leave on the electromagnetic radiation we receive from distant sources. Consider this. The light we see from distant quasars, those brilliant beacons powered by supermassive black holes, has been traveling for billions of years. Along the way, it passes through clouds of gas and dust, each one leaving its mark on the light spectrum. These marks, called absorption lines, depend on the fundamental constants of physics. If the speed of light was different when this light began its journey, or if it changed during the light's long voyage, then these absorption lines might appear slightly shifted compared to what we'd expect. The changes would be tiny, requiring the most sensitive instruments and careful analysis to detect. But they might be there, hidden in the data, waiting for someone patient enough to look. And some scientists believe they've found exactly that. In the early 2000s, a team led by John Webb at the University of New South Wales announced something remarkable. They had been studying the light from distant quasars, looking for variations in what's called the fine structure constant, a number that depends on the speed of light and other fundamental quantities. What they found was subtle, but potentially revolutionary. The fine structure constant appeared to be slightly different in the distant past compared to its value today. If confirmed, this would suggest that at least one of the fundamental constants of physics, possibly including the speed of light, has changed over cosmic time. The result was controversial, as you might expect. Other teams tried to replicate the finding, with mixed results. Some saw similar variations, others found no change at all. The debate continues to this day, with newer, more sensitive instruments providing increasingly precise measurements. But the very fact that such variations are being seriously discussed, measured, and debated represents a profound shift in how we think about the universe. The constants of physics, once thought to be as unchanging as mathematical truths, are now recognized as quantities that might evolve along with everything else in the cosmos. This raises questions that stretch far beyond the speed of light itself. If physical constants can change, what does that mean for our understanding of the laws of physics? Are these laws truly universal, or are they more like local conditions that happen to apply in our corner of space and time? Some theories suggest that the constants of physics might vary not just over time, but across space as well. In some regions of the universe, light might travel faster or slower than it does here. Gravity might be stronger or weaker. The very rules that govern matter and energy might be different. This idea, known as the multiverse hypothesis, suggests that our universe might be just one bubble in an infinite cosmic foam, each bubble with its own physical laws. In some of these universes, stars might never form because the constants don't allow nuclear fusion. In others, atoms themselves might be unstable. But we're getting ahead of ourselves. Let's return to our own universe, our own cosmic backyard, where the question of whether the speed of light is changing continues to unfold. One of the most intriguing pieces of evidence comes from a phenomenon called time dilation. Einstein's theory of relativity tells us that time runs more slowly in strong gravitational fields. This effect has been precisely measured and confirmed countless times. But what if the strength of this effect has changed over cosmic time? If the speed of light was different in the past, then the relationship between gravity and time might have been different too. Ancient light from neutron stars and black holes might carry subtle signatures of these differences, encoded in the timing of pulses and the frequency of radiation. Astronomers are now using some of the most sensitive instruments ever built to search for these signatures. The European Southern Observatory's Very Large Telescope, the Atacama Large Millimeter Array, and soon the James Webb Space Telescope are all capable of measuring light with unprecedented precision. Each observation is like reading a letter from the cosmic past, written in the language of photons and electromagnetic radiation. And some of these letters, when read carefully, seem to tell a story of a universe where the fundamental constants were not quite the same as they are today. But even if the speed of light is changing, the changes are incredibly small. We're talking about variations of perhaps 1 part in a million or less over billions of years. To put that in perspective, if the speed of light has decreased by 1 part in a million since the Big Bang, it would mean that light today is moving about 300 meters per second, slower than it did in the early universe. That's less than the speed of sound in air. Such tiny changes wouldn't affect our daily lives, or even most scientific experiments. GPS satellites would still work. Particle accelerators would still smash atoms together at nearly light speed. The effects would only become apparent when looking across the vast scales of cosmic time and distance. Yet even these minuscule changes could have profound implications for our understanding of physics. They might point toward new theories that go beyond Einstein's relativity. They might reveal connections between seemingly separate phenomena. They might even provide clues about the ultimate nature of space and time themselves. Some physicists speculate that changing constants might be a signature of extra dimensions, curled up so small that we can't directly observe them, but influencing the behavior of matter and energy in subtle ways. Others suggest that the constants might change as the universe expands, diluting some fundamental fields that determine their values. There's even a possibility that the speed of light might not change smoothly over time, but could jump suddenly during certain cosmic events. Phase transitions in the early universe, the formation of cosmic structures, or encounters with exotic forms of matter might all trigger sudden shifts in the fundamental constants. These ideas push us to the very edge of current physics, into realms where theory and speculation blend together like colors in a sunset. We're exploring questions that our current instruments can barely address, phenomena that might require entirely new mathematical frameworks to understand. And yet, this is exactly where science becomes most exciting. At the boundary between the known and the unknown, where careful observation meets bold imagination, where the universe reveals its deepest secrets to those patient enough to listen. As you lie there, letting these ideas wash over you like gentle waves, consider the light that's reaching your eyes right now. Photons from your reading lamp, perhaps, or the soft glow of a screen. Each one of these particles of light is moving at what we call the speed of light. But if the theories we've discussed tonight are correct, that speed might be just slightly different from what it was when the universe was young. The photons hitting your retina at this very moment might be traveling just a fraction slower than their ancient cousins, those first messengers of light that raced through the primordial cosmos when galaxies were still forming, and the universe was learning how to shine. It's a humbling thought, isn't it? That even something as fundamental as the speed of light might be subject to the slow drift of cosmic time. Like everything else in this vast, evolving universe, perhaps even the most basic constants are part of an ongoing story, changing and adapting as the cosmos grows older. But how would we even notice such changes? How do you measure something that's changing so slowly that billions of human lifetimes pass between detectable shifts? It's like trying to watch a mountain erode or a continent drift. The changes happen on timescales that dwarf human experience. This is where the true elegance of modern astronomy reveals itself. We don't need to wait billions of years to see how the speed of light might change over time. Instead, we look outward, across space, which is also looking backward, across time. Every photon that reaches us from a distant galaxy is a messenger from the past, carrying information about the physical conditions that existed when it began its journey. Think of it as cosmic archaeology. Instead of digging through layers of Earth to uncover ancient artifacts, astronomers dig through layers of space to uncover ancient light. Each observation is like finding a fossil, a preserved moment from the universe's deep history. And what these cosmic fossils seem to be telling us is remarkable. In the most distant galaxies we can observe, in light that has been traveling for over 13 billion years, some researchers have found subtle hints that the fundamental constants of physics were slightly different back then. The evidence is delicate, requiring years of patient observation and careful analysis. It shows up as tiny shifts in spectral lines, minute variations in the colors of starlight, barely detectable changes in the way matter and energy interact. But for those who know how to read these cosmic signals, the message is clear. The universe of the distant past was not quite the same as the universe we inhabit today. Dr. Michael Murphy, an astronomer at Swinburne University, has spent decades studying these subtle variations. Using some of the world's most powerful telescopes, he and his team have measured the light from hundreds of distant quasars, looking for signs that the fundamental constants have changed over cosmic time. What they found is both exciting and puzzling. In some directions of the sky, the constants appear to have been larger in the past. In other directions, they seem to have been smaller. It's as if the universe has a kind of grain to it, with physical laws that vary slightly depending on which way you look. If this dipole variation is real, it would suggest something extraordinary about the structure of space itself. Perhaps our universe is not perfectly uniform, but has subtle asymmetries that affect the behavior of matter and energy. Perhaps we live in a cosmic bubble with slightly different physical laws than neighboring regions of space. Or perhaps the variation is telling us something even more fundamental about the nature of physical constants. Maybe these supposedly unchanging numbers are actually fields, like the electromagnetic field or the gravitational field, that can have different values in different places and at different times. This field-like behavior of constants is predicted by some theories that attempt to unify all the forces of nature. In these theories, what we perceive as constants are actually the values of fields that settled into their current states as the universe cooled and expanded after the Big Bang. But just as water can exist as ice, liquid, or vapor, depending on temperature and pressure, these constant fields might be able to change state under extreme conditions. In the intense heat and density of the early universe, they might have had very different values than they do today. Some cosmologists have proposed that these field changes might have happened in sudden jumps, like phase transitions. Imagine the universe suddenly switching from one set of physical laws to another, the way water suddenly freezes when the temperature drops below 0 degrees. Such transitions might have occurred multiple times throughout cosmic history, each one leaving its signature in the ancient light we observe today. The varying constants that astronomers measure might be echoes of these ancient phase changes, preserved in the electromagnetic radiation that has been traveling through space for billions of years. But there's another possibility, one that's even more intriguing. What if the speed of light isn't changing randomly, but is actually controlled by the expansion of the universe itself? As the universe grows larger and larger, stretching space and diluting matter and energy, perhaps the fundamental constants are being stretched too. Like a guitar string being tuned, the fabric of spacetime might be adjusting the values of physical constants as it expands. This idea connects the changing speed of light to one of cosmology's biggest mysteries: dark energy. This mysterious force, which makes up about 70% of the universe, is causing the expansion of space to accelerate. Perhaps this same dark energy is also responsible for the slow drift of fundamental constants over cosmic time. If true, this would mean that the speed of light is intimately connected to the fate of the universe itself. As dark energy continues to drive cosmic expansion, the constants of physics might continue to evolve, potentially leading to a very different universe in the far future. Some theories predict that this evolution might accelerate as the universe ages. The constants might change more and more rapidly, eventually leading to a breakdown of the physical laws that govern matter and energy. Stars might stop shining, atoms might become unstable, and the familiar physics of our current universe might give way to something entirely new. But these are speculations about events that would occur trillions of years in the future, long after our sun has died and our galaxy has merged with others. For now, the changes in fundamental constants are so small that they barely affect anything in our local cosmic neighborhood. Still, the implications are profound. If the constants of physics can change, then the laws of nature are not as absolute as we once thought. They're more like local conditions, temporary states that happen to apply in our particular corner of space and time. This realization is both humbling and liberating. Humbling because it reminds us how much we still don't know about the universe. Liberating because it opens up new possibilities for understanding the cosmos and our place within it. Perhaps the most beautiful aspect of this research is how it demonstrates the power of human curiosity and ingenuity. We're taking light that has traveled for billions of years, light that began its journey when the universe was young and strange, and we're using it to probe the deepest questions about the nature of reality. Every photon that reaches our telescopes is a gift from the cosmic past, carrying information that no earthbound experiment could ever provide. By learning to read these messages from across space and time, we're gradually piecing together the story of how the universe has changed and evolved since the beginning. And this story is far from over. New telescopes are being built, more sensitive instruments are being developed, and theoretical physicists are creating ever more sophisticated models of how fundamental constants might behave in different cosmic environments. The James Webb Space Telescope, now peering deeper into space than ever before, is already providing new data about the distant universe. Future missions will push even further, looking for subtler signs of changing constants and testing our theories about the evolution of physical laws. Ground-based experiments are also contributing to this quest. Atomic clocks of unprecedented precision are being used to search for tiny variations in fundamental constants here on Earth. Laboratory measurements of atomic and molecular spectra are providing reference points for comparison with astronomical observations. Slowly but surely, we're building a more complete picture of how the universe works, not just in our local environment, but across all of cosmic space and time. And at the heart of this investigation is that most fundamental of questions. Is the speed of light truly constant? Or is it just another variable in the grand equation of cosmic evolution? As you drift towards sleep tonight, let your mind wander through these vast scales of space and time. Imagine photons racing across billions of light years, carrying their subtle messages about the changing nature of physical reality. Picture a universe where even the most basic constants are part of an ongoing story of growth and transformation. The speed of light, that cosmic speed limit we've trusted for so long, might be just a little bit slower tonight than it was when the first stars began to shine. And tomorrow night, it might be slower still. Part of an ancient rhythm that beats in time with the expansion of the universe itself. In this ever-changing cosmos, even the most fundamental aspects of reality are subject to the gentle drift of time. Nothing remains perfectly constant, not even constancy itself. And perhaps that's the most beautiful truth of all, that the universe is not a static, unchanging machine, but a living, evolving story in which every particle of matter and energy, every ray of light, and every moment of time plays a part. Sweet dreams, fellow travelers through this magnificent, mysterious cosmos. Tomorrow, the light will continue its ancient journey, carrying new messages from the deep past, whispering secrets about the true nature of space and time, and the ever-changing constants that govern our reality. Tonight, as you rest in this gentle space between waking and dreaming, let's drift deeper into this cosmic mystery. Because the question of whether light's speed is changing touches something profound about the nature of time itself. You see, when we talk about measuring the speed of light across cosmic history, we're really asking something much more fundamental. We're asking whether time itself flows the same way it always has, whether the rhythm of existence, the very heartbeat of reality, has remained constant since the universe began. This is where our story becomes both more complex and more beautiful. Because light doesn't travel through empty space the way we might imagine. It moves through what physicists call spacetime, that four-dimensional fabric that Einstein showed us weaves together space and time into a single, unified structure. And this fabric, this cosmic canvas on which all of existence is painted, is not static. It stretches as the universe expands. It curves around massive objects like stars and black holes. It ripples when cosmic catastrophes send gravitational waves racing across the cosmos. So, if space-time itself is changing, might not the speed of light change with it? Consider this beautiful possibility. Every photon that travels through space is like a tiny clock, keeping time according to the local properties of space-time. When light moves through regions where space is expanding rapidly, or where the fundamental fields that determine physical constants have different values, it might tick just a little differently. Dr. Jerome Barrow, the late cosmologist at Cambridge University, spent years exploring this idea. He proposed that the constants of nature might vary not just randomly, but according to specific patterns related to the geometry of space-time itself. In his models, the speed of light becomes a kind of cosmic thermometer, telling us about the temperature and density of the universe at different epochs. Imagine light as a river flowing through a landscape that changes over geological time. When the river was young, the landscape might have been steeper, allowing the water to flow faster. As the terrain gradually leveled out, the flow would slow. In the same way, light might have raced through the early universe when spacetime had a different structure, then settled into its current pace as cosmic conditions evolved. This metaphor helps us understand why detecting these changes is so challenging. Just as you wouldn't notice a river slowing down over millions of years unless you had very precise measurements, the changes in light's speed are so gradual that they're invisible on human timescales. But the universe has provided us with natural laboratories to study these effects. Pulsars, those spinning neutron stars that sweep beams of radiation across space like cosmic lighthouses, serve as incredibly precise clocks. Their pulses arrive at Earth with clockwork regularity, allowing astronomers to measure time with extraordinary accuracy. If the speed of light has changed over the years that these pulsar signals have been traveling to reach us, it would show up as tiny deviations in the arrival times of the pulses. Dr. Andrea Lohmann at Franklin and Marshall College has been leading efforts to detect exactly these kinds of variations using arrays of radio telescopes around the world. The precision required for such measurements is almost beyond imagination. We're looking for changes of nanoseconds in signals that have been traveling for thousands of years. It's like trying to detect whether a clock on the other side of the world is running 1 second slow after timing it for a single day. Yet this is exactly the kind of challenge that modern astronomy excels at. By combining observations from multiple telescopes, using sophisticated computer analysis, and carefully accounting for all known sources of error, researchers can achieve measurement precision that would have seemed impossible just a few decades ago. And what they're finding is intriguing. Some pulsar timing studies have detected small anomalies that could be explained by varying fundamental constants. Other studies find no such variations. The data is complex, sometimes contradictory, always requiring careful interpretation. This uncertainty is not a weakness of science, but one of its greatest strengths. It forces researchers to be cautious, to double-check their results, to consider alternative explanations. In the realm of changing constants, where the implications are so profound, this careful skepticism is essential. Dr. Thibault Damour at the Institut des Hautes Études Scientifiques in France has developed some of the most sophisticated theoretical frameworks for understanding how fundamental constants might vary. His work shows that even tiny changes in these constants could have cascading effects throughout physics. If the speed of light changes, then so does the fine structure constant, which determines the strength of electromagnetic interactions. This would affect how atoms absorb and emit light, how chemical bonds form, even how nuclear reactions proceed in stars. The universe would literally work differently at the most basic level. But these differences would be subtle, at least for the small changes we're considering. Stars would still shine, planets would still orbit, life could still evolve. The changes would be more like a gentle tuning of the cosmic orchestra, adjusting the pitch without changing the melody. In fact, some researchers have suggested that varying constants might actually be necessary for the universe to remain habitable over cosmic time. As the universe expands and cools, the changing constants might compensate for these environmental shifts, keeping conditions suitable for complexity and life. This idea connects to one of the deepest questions in cosmology, the so-called fine-tuning problem. Many of the fundamental constants seem to be precisely adjusted to allow for the existence of stars, planets, and living beings. Change them by even small amounts, and the universe might be a cold, empty place where nothing interesting ever happens. Some physicists argue that this fine-tuning is evidence for a multiverse, where our universe is just one of countless others with different physical laws. We exist in this particular universe precisely because its constants happen to allow for our existence. But if constants can vary over time, there's another possibility. Perhaps the universe started with random values for its physical constants. But those constants evolved over cosmic time toward values that support complexity and life. The universe might have tuned itself through its own evolution. This is still highly speculative, of course, but it illustrates how the question of changing constants connects to some of the biggest mysteries in physics and cosmology. Are we alone in the universe? Is our existence a cosmic accident, or somehow inevitable? How did the laws of physics come to have the precise values we observe? As you let these questions drift through your mind like clouds across a night sky, consider how far we've come in our understanding of the cosmos. A century ago, we didn't even know that other galaxies existed. The idea that fundamental constants might change over time would have seemed absurd. Today, we routinely observe galaxies billions of light years away, peer into the cosmic microwave background, to study the universe when it was just 380,000 years old, and detect gravitational waves from colliding black holes. We've learned to read the history of the cosmos in the light that reaches our telescopes. And that history is still being written. Every night, as Earth turns and new regions of sky come into view, our telescopes gather fresh photons from across the universe. Each observation adds another data point to our understanding of how physical constants behave across space and time. The Atacama Large Millimeter Array in Chile, a collection of 66 radio telescopes working together, can measure the frequencies of distant molecular emissions with extraordinary precision. These measurements provide some of the most sensitive tests of whether fundamental constants have changed over cosmic time. Similarly, the European Southern Observatory's Very Large Telescope uses sophisticated spectrographs to analyze the light from distant quasars, looking for tiny shifts in atomic absorption lines that might indicate varying constants. These instruments can detect changes of just a few parts per million, pushing the boundaries of what's measurable. But perhaps the most exciting developments are yet to come. The next generation of extremely large telescopes, with mirrors 30 meters or more in diameter, will have the sensitivity to detect even smaller variations in fundamental constants. Space-based missions dedicated to precision astrometry will measure the positions and motions of stars with unprecedented accuracy. And theoretical physics continues to evolve as well. String theory, loop quantum gravity, and other approaches to unifying general relativity with quantum mechanics all make predictions about how fundamental constants might behave in different cosmic environments. Some string theories suggest that our universe has extra dimensions beyond the 3 spatial dimensions we experience directly. These hidden dimensions might be slowly changing size as the universe evolves, causing the apparent values of fundamental constants to drift over time. Other theories propose that what we call constants are actually fields, similar to the Higgs field that gives particles their mass. These constant fields might have been trapped in high-energy states in the early universe, then slowly relaxed to their current values as cosmic conditions changed. There's even speculation that the constants might undergo sudden phase transitions, like water suddenly freezing. These transitions could be triggered by cosmic events such as the collision of domain walls, topological defects in spacetime left over from the early universe. If such transitions occurred, they would leave distinctive signatures in the cosmic microwave background and other observable phenomena. Future missions designed to study the early universe with greater precision might be able to detect these signatures, providing direct evidence for changing constants. But even if we never find definitive proof that fundamental constants vary, the search itself is transforming our understanding of physics. It's forcing us to question assumptions we've held for generations, to develop new theoretical frameworks, to push the boundaries of experimental precision. The very act of looking for changing constants has led to discoveries we never expected. Studies of distant quasars have revealed new details about the structure of intergalactic space. Precision measurements of atomic spectra have improved our understanding of quantum mechanics. pulsar timing arrays have opened new windows into gravitational wave astronomy. This is how science progresses, not through sudden revelations, but through patient accumulation of knowledge, careful questioning of established ideas, and willingness to follow the evidence wherever it leads. Each small step forward opens new questions, new possibilities, new horizons to explore. Tonight, as photons from distant stars stream through your window, carrying messages from across the cosmos, remember that you're witnessing the latest chapter in an ancient story. The light that's reaching your eyes began its journey perhaps hundreds or thousands of years ago, when the fundamental constants of physics might have had slightly different values. Those photons have traveled through expanding space, past countless other stars and galaxies, carrying with them the imprint of the physical conditions they encountered along the way. They're messengers from a universe that was subtly different from the one we inhabit today, and tomorrow night new messengers will arrive, carrying fresh information about the evolving nature of physical reality. The universe is constantly revealing new aspects of itself to those patient enough to observe and wonder. In this gentle exploration of cosmic mysteries, we find something deeply human: the desire to understand our place in the universe, to know how the cosmic story began and where it might be heading. The changing speed of light, if it's real, is just one thread in this vast tapestry of cosmic evolution. But it's a thread that connects us to the deepest questions about the nature of existence itself. Why do the laws of physics have the values they do? How did the universe come to be so precisely tuned for complexity and life? Are we part of a grand cosmic experiment in which the rules themselves are still being written? As you drift towards sleep, let your imagination wander through these vast scales of space and time. Picture the universe as a living, breathing entity, constantly adjusting and evolving, fine-tuning its own parameters as it grows older and more complex. The speed of light, that fundamental constant we've relied upon for so long, might be just one voice in a cosmic symphony that's been playing since the beginning of time. Each note slightly different from the last, each movement building towards some unknown crescendo in the far future. And we, conscious observers in this evolving cosmos, are privileged to witness this grand performance. We can measure the subtle changes in the cosmic constants, decode the messages carried by ancient light, and piece together the story of how the universe has transformed itself over billions of years. This is the true magic of modern astronomy. Not just the pretty pictures of distant galaxies or the dramatic discoveries of new planets, but the patient work of understanding how the deepest laws of nature themselves might be part of the cosmic story. Whether the speed of light is truly changing remains an open question. The evidence is subtle, the measurements challenging, the implications profound. But the search itself has already taught us so much about the nature of physical reality and our methods for exploring it. Rest now in the knowledge that the universe continues its ancient dance, adjusting its rhythms with each passing cosmic moment. The constants that govern reality might be slowly drifting, like a river meandering across a vast plain, carrying us all towards some distant cosmic sea. And in the morning, when you wake to a world where light still travels at nearly 300 million meters per second, remember that this seemingly eternal constant might be just a little different than it was when you closed your eyes. The universe never truly stops evolving, never stops surprising us with its subtle complexities and hidden depths. Sweet dreams, fellow travelers in this magnificent cosmos, where even the speed of light might be learning new steps in the eternal dance of existence. But what if these tiny changes we're discussing aren't as random as they might seem? What if there's a deeper pattern hidden within the cosmic drift of constants, a rhythm that echoes through the very foundation of reality itself? Dr. Claudia de Ram at Imperial College London has been exploring precisely this possibility. Her work suggests that the speed of light might not change uniformly across all of space, but could vary according to the local curvature of space-time itself. In regions where gravity is stronger, where massive objects bend the fabric of reality more severely, light might behave differently than it does in the gentle cosmic voids between galaxies. Think of it this way. Imagine you're walking across a landscape that's constantly shifting beneath your feet. Sometimes the ground is firm and level, allowing you to maintain a steady pace. Other times it's soft and uneven, forcing you to slow down or speed up. Light traveling through the cosmos might experience something similar as it encounters different gravitational environments. This idea has profound implications for how we understand the structure of the universe. If light travels at slightly different speeds in different cosmic neighborhoods, then our measurements of distance and time might need careful recalibration. The universe might be subtly larger or smaller than we thought, older or younger than our current estimates suggest. But here's where the story becomes even more intriguing. Some theoretical physicists propose that these variations in the speed of light might actually be responsible for creating the large-scale structure we see in the universe today. The cosmic web of galaxies and dark matter, the vast filaments and voids that stretch across billions of light years, might all trace back to tiny fluctuations in fundamental constants during the universe's earliest moments. Dr. Nemanja Kaliper at the University of California, Davis, has developed models where changing constants act like seeds, growing into the cosmic structures we observe today. In his scenarios, regions where the speed of light was slightly higher in the early universe would evolve differently than regions where it was lower, eventually leading to the clumpy, web-like distribution of matter we see around us. It's a beautiful idea that connects the smallest scales of physics with the largest structures in the cosmos. The speed of light, varying by perhaps just a few parts per billion, might have sculpted the very architecture of reality over billions of years of cosmic evolution. As you rest there, letting these concepts wash over you like gentle waves, consider how this connects to one of astronomy's most beautiful discoveries. When we look at the cosmic microwave background, that faint afterglow of the Big Bang, we see tiny temperature fluctuations across the sky. These fluctuations, just a few millionths of a degree, were the seeds from which all cosmic structure grew. But what created these primordial fluctuations in the first place? The standard explanation involves quantum fluctuations stretched to cosmic scales during a period of rapid expansion called inflation. But perhaps the varying speed of light played a role as well, adding its own subtle signature to the cosmic microwave background. Future missions designed to study this ancient light with even greater precision might be able to detect these signatures. The European Space Agency's Planck satellite has already provided the most detailed map of the cosmic microwave background ever created. Its successor missions will push even deeper, looking for the faintest traces of varying constants in the universe's baby picture. But the search for changing constants isn't limited to distant observations. Here on Earth, in laboratories around the world, physicists are conducting incredibly precise experiments to detect any variations in fundamental constants that might be occurring right now in real time. The most sensitive of these experiments involve atomic clocks, devices so precise that they lose only 1 second every 15 billion years. By comparing different types of atomic clocks over long periods, researchers can search for tiny drifts in the constants that determine atomic transition frequencies. Dr. Mariana Safronova at the University of Delaware leads efforts to use these atomic clock networks to detect varying constants. Her team has developed theoretical frameworks that predict exactly how different constants would affect different types of clocks, allowing them to disentangle the various possibilities. What they're looking for are correlated changes across multiple clock systems. If the speed of light is changing, it should affect all electromagnetic phenomena in predictable ways. By monitoring many different atomic transitions simultaneously, researchers can build up a detailed picture of how, or whether, the fundamental constants are evolving. So far, these experiments have found no evidence for changing constants on human timescales. But they've pushed the precision of such measurements to extraordinary levels, setting limits that constrain how fast any changes could be occurring. The constants of physics, if they're changing at all, are doing so incredibly slowly. This stability on short timescales doesn't rule out changes over cosmic history. It's perfectly possible that constants drift so slowly that billions of years are required to produce measurable effects. The atomic clock experiments complement the astronomical observations, providing a complete picture of how constants behave across all accessible timescales. There's something deeply satisfying about this multi-pronged approach to fundamental questions. We're using the most distant galaxies and the most precise laboratory instruments, the largest telescopes and the smallest atomic transitions, all in service of understanding whether the basic laws of physics are truly universal and eternal. Dr. Victor Flambam at the University of New South Wales has spent decades developing the theoretical foundation for these searches. His work shows how varying constants would leave distinctive fingerprints in atomic spectra, both in laboratory measurements and in light from distant astronomical sources. One of the most intriguing aspects of Flambam's research involves what he calls the many-multiplet method. By studying multiple atomic transitions simultaneously, it becomes possible to determine not just whether constants are changing, but which specific constants are responsible for any observed variations. This is crucial because the fundamental constants are all interconnected. The speed of light, the electron charge, Planck's constant, and other quantities are woven together in the mathematical fabric of quantum mechanics and relativity. A change in one constant might affect others, creating complex patterns of variation that require careful analysis to unravel. Imagine trying to tune a complex musical instrument, where adjusting one string affects the tension in all the others. The fundamental constants of physics are similarly coupled, and understanding their relationships is key to interpreting observations of cosmic variation. Some of the most exciting recent developments in this field involve the discovery of molecular transitions that are exceptionally sensitive to changing constants. Dr. Wim Ubachs at Vrije Universiteit Amsterdam has identified specific molecular lines in hydrogen that would shift dramatically if fundamental constants were different. These molecular transitions act like cosmic amplifiers, magnifying tiny changes in constants into easily detectable shifts in spectral lines. By studying these transitions in light from distant quasars, astronomers can achieve unprecedented sensitivity to varying constants across cosmic time. The hydrogen molecule is particularly important because it's the most abundant molecule in the universe. Wherever we look in space, we find hydrogen clouds that can serve as natural laboratories for testing the constancy of physical laws. Each cloud is like a cosmic laboratory that has been running experiments on fundamental physics for millions or billions of years. But hydrogen isn't the only molecule that can probe changing constants. Dr. Michael Murphy's team has identified numerous other molecular species that show different sensitivities to various physical constants. By studying multiple molecules simultaneously, they can build up a comprehensive picture of how constants might be varying across space and time. This molecular approach has revealed some of the most stringent limits on varying constants ever achieved. In some cases, researchers can rule out changes of more than a few parts in a billion over billions of years of cosmic evolution. Such precision would have been unimaginable just a few decades ago. Yet even with these incredibly tight constraints, there's still room for the subtle variations that some theories predict. The universe might be changing in ways so gentle that only the most sensitive measurements can detect them, like listening for whispers in a vast, quiet cathedral. As you drift deeper into contemplation, consider how this research is changing our perspective on the nature of scientific laws themselves. We've grown accustomed to thinking of physical constants as eternal, unchanging pillars that support the structure of reality. But perhaps they're more like the flowing water of a river, maintaining their essential character while constantly adapting to the landscape through which they move. This shift in perspective has philosophical implications that extend far beyond physics. If the laws of nature themselves can evolve, what does that tell us about the relationship between mind and cosmos, between consciousness and the physical world that gives rise to it? Some philosophers of science argue that varying constants point toward a more dynamic, organic view of the universe. Rather than a cosmic machine operating according to fixed rules, we might inhabit a living system that grows and learns and adapts over cosmic time. Dr. Lee Smolin at the Perimeter Institute for Theoretical Physics has proposed that the universe might actually evolve through a process resembling natural selection. Universes with physical constants that allow for complexity and reproduction would be more likely to spawn new universes, leading to a gradual optimization of cosmic parameters over time. This cosmological natural selection hypothesis is highly speculative, but it illustrates how questions about varying constants connect to the deepest mysteries of existence. Why does the universe exist? Why does it have the particular laws and constants that we observe? Are we witnessing the result of some vast, cosmic, evolutionary process? These questions may not have answers that we can access through current scientific methods, but the very act of asking them, of pushing our understanding to its limits, reveals something profound about the human capacity for wonder and discovery. Tonight, as ancient starlight streams through your window, remember that you're connected to this cosmic quest for understanding. Every photon that reaches your eyes has traveled through a universe where the fundamental constants might be slowly shifting, where the speed of light itself might be part of an ongoing story of cosmic evolution. The light from the nearest star beyond our sun, Proxima Centauri, began its journey over 4 years ago. If the speed of light has changed during that time, the change would be unimaginably small, perhaps a few parts in a trillion. Yet even such tiny variations, accumulated over billions of years and across billions of light years, might hold the key to understanding how our universe really works. And what of the future? If constants are indeed changing, what might the universe look like in billions of years to come? Will the speed of light continue its gradual drift, eventually reaching values so different from today that the physics of the far future becomes unrecognizable? Some cosmologists speculate about a distant epoch when the fundamental constants might undergo dramatic phase transitions, suddenly jumping to new values as cosmic conditions cross critical thresholds. Such transitions could reshape the entire universe, making new forms of matter and energy possible while rendering others unstable. But these are events so far in the future that the sun will have long since died, our galaxy will have merged with Andromeda, and the night sky will look completely different. The changes we're discussing tonight unfold on timescales that dwarf not just human history, but the entire history of complex life on Earth. There's something both humbling and comforting about this cosmic perspective. Our daily concerns, our fleeting existence, our brief moment of consciousness in the vast sweep of cosmic time. All of this is embedded within a universe that operates according to laws so stable that they've remained essentially unchanged throughout the history of life itself. Even if the speed of light is drifting slowly toward new values, even if the fundamental constants are part of an ongoing cosmic evolution, the changes are so gradual that they form a stable foundation for everything we know and love. The atoms in our bodies, the chemistry of life, the nuclear reactions that power the sun, all of these processes can rely on physical constants that remain effectively unchanged across the timescales that matter for biological existence. Yet the possibility of changing constants also offers a kind of cosmic hope. It suggests that the universe is not a static, predetermined machine, but a dynamic system capable of growth and transformation. If the laws of physics themselves can evolve, then perhaps the future holds possibilities we haven't yet imagined. Dr. Andreas Albrecht, one of the pioneers of varying constant cosmology, often speaks about this dual nature of cosmic evolution. The universe must be stable enough to allow for the development of complexity and life, yet dynamic enough to avoid stagnation and decay. Slowly varying constants might provide exactly this balance, offering stability on short timescales while permitting gradual optimization over cosmic ages. As you settle deeper into rest, let your imagination follow this thread of possibility. Picture a universe that's constantly fine-tuning itself, adjusting its fundamental parameters in response to the structures and processes that emerge within it. The speed of light, the strength of gravity, the masses of particles, all gradually evolving toward values that maximize the universe's capacity for beauty, complexity, and perhaps even consciousness. This is still speculation, of course. The evidence for varying constants remains subtle and contested, but the very fact that we can measure such variations, that we can peer across billions of years of cosmic history and detect changes of a few parts per million in the fundamental laws of physics, speaks to the extraordinary power of human curiosity and ingenuity. We are, as Carl Sagan once said, a way for the cosmos to know itself. Through our telescopes and atomic clocks, our theoretical frameworks and patient observations, the universe is slowly revealing its deepest secrets. And among those secrets might be the surprising truth that even the most fundamental aspects of reality are part of an ongoing story of cosmic becoming. Tonight, rest in the gentle certainty that this story continues. Somewhere in a distant galaxy, light is beginning a journey that will take billions of years to complete. That light carries within its wavelength and frequency the imprint of physical constants that might be slightly different from the ones we measure today. By the time that light reaches some future Earth, if Earth still exists, those who observe it might find that the speed of light itself has drifted to new values. They might live in a universe where the fundamental constants have evolved just enough to open new chapters in the cosmic story. But for now, in this moment, in this gentle space between waking and sleeping, the speed of light maintains its patient constancy. It races through the cosmos at 92,458 meters per second, give or take perhaps a few parts per billion, carrying messages between stars and galaxies, weaving together the fabric of space and time. And tomorrow, as you wake to a world where light still illuminates the morning sky, remember that you've been part of this ancient conversation between mind and cosmos, this ongoing quest to understand whether the deepest laws of nature are as eternal as they seem, or whether they too are travelers on the long journey of cosmic evolution. The speed of light, that cosmic constant we've trusted for so long, might be whispering secrets about the true nature of time and space and change. All we have to do is listen carefully enough to hear them. But what does it mean, really, for something as fundamental as the speed of light to change? How would we even recognize such a shift if it happened gradually over millions of human generations? As you rest there, breathing slowly, let yourself imagine what this might feel like from the perspective of light itself. Picture a photon born in the heart of a distant star billions of years ago. At the moment of its creation, it begins racing through space at what we now call the speed of light. But perhaps, in that ancient epoch, the very fabric of space-time was subtly different. The photon moves through a universe where the electromagnetic field has a slightly different strength, where the quantum vacuum fluctuates at a marginally different frequency. As eons pass and the universe expands, as galaxies drift apart and dark energy stretches the cosmic web, perhaps the photon finds itself moving through a gradually transforming medium. Not slower or faster in any dramatic sense, but with tiny, incremental adjustments that accumulate over cosmic time, like sediment settling on an ocean floor. Dr. Sean Carroll at Caltech has explored how such changes might manifest in the quantum fields that permeate all of space. These fields, invisible to our senses but fundamental to physics, could be slowly evolving as the universe ages. Like a vast musical instrument being gradually retuned, the cosmos might be adjusting its harmonics in ways too subtle for any single generation to detect. This brings us to one of the most beautiful aspects of this research. We're not just asking whether numbers on our instruments are changing. We're probing the deeper question of whether reality itself has a kind of memory, a capacity for growth and adaptation that extends beyond the familiar biological realm into the very foundations of physics. Consider the implications if this proves true. It would mean that the universe we inhabit today is not quite the same universe that existed when the first stars formed. The photons reaching us from those primordial epochs would be messengers from a subtly different cosmic era, carrying information about physical laws that no longer apply in quite the same way. Dr. Max Tegmark at MIT has calculated that even changes of 1 part in a billion could accumulate over cosmic time to produce measurable effects. His work shows how the seemingly impossible task of detecting such tiny variations becomes feasible when you have billions of years of cosmic evolution to amplify the signal. Think of it like watching the hour hand of a clock. In any given moment, the movement is imperceptible, but step back far enough in time, and the motion becomes obvious. Similarly, the evolution of fundamental constants might be invisible on human timescales, while remaining clearly detectable across the vast reaches of cosmic history. This perspective has led some researchers to propose entirely new ways of thinking about physical laws. Rather than eternal, unchanging rules imposed on the universe from outside, perhaps these laws emerge from within the cosmic system itself, evolving and adapting as the universe grows in complexity and age. Dr. Roberto Busso at UC Berkeley has suggested that what we call constants might actually be slowly varying fields, similar to the fields that give particles their mass or create electromagnetic forces. These constant fields could have their own dynamics, their own evolutionary pathways, their own responses to the changing cosmic environment. If true, this would represent a profound shift in how we understand the relationship between laws and phenomena in physics. Instead of laws governing matter and energy from some transcendent realm, we might have a more integrated picture where laws and phenomena co-evolve together, each shaping the other in an ongoing cosmic dance. This idea resonates with some of the deepest questions in cosmology. Why do the fundamental constants have the precise values we observe? Why is the universe so finely tuned for the existence of stars, planets, and living beings? Perhaps because these constants have been slowly adjusting themselves over cosmic time, settling into values that maximize the universe's capacity for complexity and beauty. It's a speculative idea, certainly, but it's grounded in real physics and supported by increasingly sophisticated observations. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, is providing new insights into how fundamental fields behave under extreme conditions. These experiments help theorists understand how constants might evolve in different cosmic environments. Meanwhile, gravitational wave detectors like LIGO and Virgo are opening entirely new windows into the cosmos. These instruments detect ripples in spacetime itself, created when massive objects like black holes collide billions of light years away. If fundamental constants are changing, these gravitational waves might carry subtle signatures of that evolution. Dr. Bangalore Sathyaprakash at Penn State has been developing methods to search for such signatures in gravitational wave data. His work shows how the waveforms produced by colliding black holes depend sensitively on the values of fundamental constants. By analyzing these waveforms with sufficient precision, researchers might be able to detect variations in constants across cosmic time. The beauty of this approach is that gravitational waves travel through space virtually unimpeded. Unlike light, which can be absorbed or scattered by intervening matter, gravitational waves carry pristine information about the physical conditions that existed when they were created. They're like messengers from the deepest depths of spacetime, carrying news about the fundamental nature of gravity and geometry. As you drift deeper into contemplation, consider how these different approaches are converging toward a more complete understanding of cosmic evolution. Radio telescopes studying distant quasars, atomic clocks measuring time with unprecedented precision, particle accelerators probing the quantum vacuum, gravitational wave detectors listening to the songs of colliding black holes. All are contributing pieces to the same vast puzzle. Each method has its own strengths and limitations. Quasar spectroscopy can look far back in cosmic time, but requires careful analysis to separate genuine constant variations from other effects. Atomic clocks provide incredible precision, but only over relatively short timescales. Gravitational waves offer pristine information, but are challenging to detect and analyze. By combining all these approaches, researchers are building the most comprehensive picture ever assembled of how fundamental constants behave across space and time. It's a testament to the power of international scientific collaboration, with teams around the world sharing data, techniques, and insights. Dr. John Webb, whose early work first suggested that constants might be varying, often speaks about the patience required for this kind of research. Unlike some areas of physics where dramatic discoveries can happen overnight, the search for varying constants requires years or even decades of careful observation and analysis. The signals being sought are so subtle that they can easily be masked by instrumental effects, atmospheric variations, or simple measurement errors. Each claimed detection must be carefully verified, each null result thoroughly understood. Progress comes slowly, one careful measurement at a time. But this methodical approach has its own rewards. When a result finally emerges from such careful analysis, when multiple independent teams reach similar conclusions using different methods, the confidence level is extraordinarily high. The varying constant community has learned to be skeptical of dramatic claims, but this skepticism makes their eventual conclusions all the more robust. Some of the most intriguing recent results come from studies of white dwarf stars, the dense remnants left behind when sun-like stars exhaust their nuclear fuel. These stellar corpses are natural laboratories for testing fundamental physics under extreme conditions. Dr. Matthew Barstow at the University of Leicester has been studying the atmospheres of white dwarf stars, looking for spectral lines that would be sensitive to varying constants. The intense gravity and magnetic fields around these objects create conditions unlike anything achievable in terrestrial laboratories. What makes white dwarf studies particularly interesting is their potential to test how constants behave in strong gravitational fields. Einstein's theory of general relativity predicts that gravity can affect the passage of time, and some theories suggest it might also influence the values of fundamental constants. If constants do vary with gravitational field strength, white dwarf stars would be ideal places to observe such effects. The gravitational fields around these objects are millions of times stronger than Earth's gravity, potentially amplifying any constant variations to detectable levels. The results so far are tantalizing but inconclusive. Some white dwarf studies have found hints of anomalous spectral line shifts that could indicate varying constants. Others have found no such evidence. As with many aspects of varying constant research, the jury is still out, but each new observation adds another piece to the puzzle. Even null results are valuable, as they help constrain how much constants could be varying while remaining consistent with observations. Science progresses as much through ruling out possibilities as through confirming them. This patient accumulation of evidence reflects something profound about the nature of cosmic mysteries. The universe doesn't reveal its secrets easily or quickly. It requires sustained effort, careful observation, and willingness to follow subtle clues wherever they might lead. As you rest in this gentle exploration of cosmic mysteries, let your mind wander through the vast scales of space and time where these investigations unfold. From the quantum fluctuations of the vacuum to the expansion of the universe itself, from the cores of atoms to the event horizons of black holes, the question of varying constants touches every level of physical reality. Perhaps most remarkably, it connects the smallest and largest scales in unexpected ways. The behavior of individual photons depends on the same fundamental constants that govern the evolution of galaxies. Changes too small to affect a single atom might accumulate over cosmic time to reshape the structure of the entire universe. This unity across scales is one of the most beautiful aspects of modern physics. The same mathematical frameworks that describe quantum mechanics also appear in cosmology. The constants that determine how atoms absorb light also influence how stars form and galaxies evolve. Dr. Paul Davies at Arizona State University has written extensively about this deep interconnectedness in physics. His work shows how varying constants would create a kind of cosmic butterfly effect, where tiny changes in the fundamental parameters could eventually lead to dramatically different cosmic outcomes. Imagine a universe where the speed of light was just slightly different in the early cosmic epochs. Perhaps stars would have formed differently, burning their fuel at different rates. Galaxies might have evolved along different pathways. The cosmic web of dark matter and ordinary matter might have taken on entirely different structures. In such a universe, the night sky might look completely alien to us. Different types of stars, different galactic structures, perhaps even different forms of matter and energy that don't exist in our current cosmic environment. This speculative exploration helps us appreciate how finely balanced our universe appears to be. The constants of physics seem to be adjusted to just the right values to allow for the rich variety of structures we observe. Stars that live long enough for planets to form, nuclear reactions that create the heavy elements necessary for life, gravitational forces that hold galaxies together without crushing everything into black holes. If these constants are indeed slowly varying, it raises profound questions about cosmic destiny. Are we living in a special epoch when the constants happen to have values conducive to complexity and life? Or might the universe be gradually evolving toward even more interesting configurations in the distant future? Some cosmologists have proposed that the universe might be heading toward what they call a complexity maximum, an epoch billions of years from now when the constants will have evolved to values that maximize the universe's capacity for information processing and organization. It's a beautiful vision of cosmic purpose, suggesting that the universe might be slowly optimizing itself for consciousness and complexity. But it remains highly speculative, far beyond what current observations can confirm or deny. For now, we can only continue the patient work of observation and measurement, slowly mapping how the fundamental constants behave across cosmic space and time. Each new data point brings us slightly closer to understanding whether the deepest laws of physics are truly eternal or whether they too are part of the grand story of cosmic evolution. Tonight, as you drift towards sleep, let yourself feel connected to this ongoing quest for understanding. Somewhere in a distant laboratory, an atomic clock is ticking with precision beyond imagination, searching for the tiniest variations in fundamental constants. Somewhere else, a radio telescope is gathering ancient light from a quasar billions of light years away, analyzing that light for subtle signs of cosmic evolution. The photons reaching your eyes right now, whether from a bedside lamp or the glow of stars through your window are part of this vast experimental apparatus. They carry information about the fundamental constants of physics, encoded in their wavelengths and frequencies, their interactions with matter and fields. Each blink of your eyes, each breath you take, each heartbeat that marks the passage of time, all of these biological rhythms unfold within a cosmic framework governed by physical constants that might, just might, be slowly drifting toward new values as the universe ages and evolves. The speed of light, that cosmic constant we've trusted for so long, might be participating in this gradual transformation. Racing through space at nearly 300 million meters per second, yet perhaps moving just a tiny bit differently than it did when the first galaxies formed in the cosmic dawn. Whether this cosmic drift is real remains an open question. The evidence is subtle, the measurements challenging, the implications profound. But the very fact that we can probe such deep questions, that we can peer across billions of years of cosmic history and detect changes measured in parts per billion, speaks to something remarkable about human curiosity and ingenuity. We are witnesses to the universe's ongoing story, conscious observers capable of recognizing patterns and changes across scales of space and time that dwarf individual experience. Through our instruments and theories, our patient observations and careful analysis, the cosmos is slowly revealing whether its most fundamental properties are as eternal as they seem. Rest now in the knowledge that this cosmic investigation continues while you sleep. The universe keeps its secrets closely, but it does eventually share them with those persistent enough to keep asking the right questions. And tomorrow, when you wake to a world where light still travels at its familiar speed, remember that you've been part of humanity's greatest adventure. The quest to understand whether the deepest laws of nature are written in stone, or whether they too dance to the rhythm of cosmic time. Sweet dreams, fellow travelers in this magnificent universe, where even the speed of light might be learning new steps in the eternal choreography of existence. But perhaps the most profound question isn't whether the speed of light is changing, but what that change might tell us about the deeper nature of reality itself. As you settle deeper into this quiet contemplation, let your mind drift toward an even more fundamental mystery. What if the speed of light isn't just a cosmic speed limit, but something more like a cosmic memory? Picture this possibility. Every photon that travels through space carries with it not just energy and momentum, but information about the physical conditions it has encountered along its journey. The quantum fields it has interacted with, the gravitational wells it has climbed out of, the dark energy that has stretched the space through which it moves. Dr. Stefan Alexander at Brown University has proposed that the speed of light might function as a kind of cosmic barometer, responding to changes in the overall energy density of the universe. As the cosmos expands and cools, as matter becomes more dilute and dark energy becomes more dominant, perhaps the fundamental constants adjust themselves accordingly. This would mean that the speed of light we measure today is not some arbitrary value imposed on the universe from outside, but rather an emergent property that reflects the current state of cosmic evolution. Like the temperature of a vast ocean that slowly changes with the seasons, the speed of light might be slowly responding to the changing cosmic climate. Such a perspective transforms our understanding of what physical constants really are. Instead of eternal, unchanging pillars that hold up the structure of reality, they become dynamic variables that participate in the universe's ongoing story of growth and transformation. Consider how this might work in practice. In the dense, hot universe of the cosmic dawn, when matter and energy were packed much more tightly than they are today, the quantum vacuum itself would have had different properties. The fields that determine electromagnetic interactions would have oscillated with different frequencies, creating slightly different values for what we call fundamental constants. As the universe expanded and cooled, as the first stars formed and began to shine, As galaxies assembled themselves from primordial gas clouds, these field values would have gradually shifted. Not dramatically, not suddenly, but with the patient persistence of cosmic time itself. Dr. João Magalhães, whose variable speed of light theories we touched on earlier, often describes this process using the metaphor of a symphony. The early universe played its music at a different tempo than the cosmos we inhabit today. The same fundamental melodies, but performed with slightly different timing, creating harmonies that have slowly evolved over billions of years. This musical metaphor is more than just poetic language. It reflects a deep mathematical truth about how quantum fields behave in different cosmic environments. The equations that govern these fields are indeed like musical scores, with solutions that depend sensitively on the background conditions in which they're embedded. As you let this idea resonate through your thoughts, consider what it might mean for our understanding of cosmic history. Every major transition in the universe's evolution, the end of inflation, the formation of the first atoms, the birth of the first stars, might have left its signature in the gradually changing values of fundamental constants. These transitions would be like chapter breaks in the cosmic story, moments when the universe shifted from one phase of evolution to another. And if we're clever enough, patient enough, precise enough in our measurements, we might be able to read these chapter breaks in the light that reaches us from across cosmic time. Some of the most intriguing possibilities involve what cosmologists call phase transitions in the early universe. These are moments when the cosmos underwent sudden changes in its fundamental state, like water suddenly freezing into ice, or steam suddenly condensing into droplets. During such transitions, the fields that determine physical constants might have jumped from one value to another, creating what theorists call domain walls or cosmic strings. These exotic structures, if they exist, would be like fossil remains of the early universe's growing pains, preserved in the fabric of spacetime itself. Dr. Tanmay Vachaspati at Arizona State University has spent years studying how such cosmic defects might affect the propagation of light through space. His calculations show that encounters with these structures could leave subtle imprints on electromagnetic radiation, creating patterns that might still be detectable in light from distant sources. The search for such patterns represents one of the most ambitious projects in modern cosmology. Researchers are essentially trying to read the universe's autobiography, written in the faint whispers of ancient light that has been traveling through space since cosmic dawn. But this cosmic autobiography isn't written in any human language. It's encoded in the quantum properties of photons, in the precise frequencies at which atoms absorb and emit radiation, in the subtle correlations between different wavelengths of light. Learning to read this language has required developing entirely new mathematical tools and observational techniques. It's like trying to decode a message written in a script you've never seen before, using an alphabet that spans the entire electromagnetic spectrum. Dr. Anthony Lewis at the University of Sussex has been at the forefront of developing the computational tools needed for this cosmic archaeology. His software packages allow researchers to compare theoretical predictions with observational data, searching for the faint signatures of varying constants in the cosmic microwave background and other astronomical observations. The precision required for such work is almost beyond imagination. Researchers are looking for changes of perhaps 1 part in a billion, buried in data sets that contain millions of individual measurements. It's like trying to detect whether a single grain of sand has been added to a beach by measuring the weight of the entire shoreline. Yet this is exactly the kind of challenge that modern astronomy excels at. By combining observations from multiple telescopes, using sophisticated statistical analysis techniques, and carefully accounting for all known sources of error, researchers can achieve measurement precision that would have seemed impossible just a few decades ago. The Planck satellite which operated from 2009 to 2013, provides a perfect example of this precision. This European Space Agency mission mapped the cosmic microwave background with such accuracy that it could detect temperature variations of just a few millionths of a degree across the sky. Hidden within this exquisitely detailed map are subtle patterns that encode information about the physical conditions in the early universe. If fundamental constants were different back then, those differences would have left their mark on the cosmic microwave background in ways that careful analysis can potentially reveal. Dr. Levon Pogosyan at Simon Fraser University has been leading efforts to extract this information from Planck data. His team has developed techniques for separating the signatures of varying constants from other effects that might create similar patterns in the cosmic microwave background. Their results so far have been tantalizing but inconclusive. Some analyses suggest hints of variation in fundamental constants, while others find no such evidence. The signals being sought are so subtle that they push current measurement techniques to their absolute limits. But this is how science progresses at the frontiers of knowledge. Each new measurement, each refined analysis technique, each improved theoretical model brings us slightly closer to understanding whether the fundamental constants of physics are truly constant or whether they participate in the cosmic story of evolution and change. As you rest in this gentle exploration of cosmic mysteries, let your imagination wander through the vast scales of space and time where these investigations unfold. Picture the cosmic microwave background as a vast tapestry woven from the light of creation itself, with subtle patterns that might encode the secret history of how physical laws have evolved over cosmic time. Every point of light in that ancient glow is a messenger from an epoch when the universe was just 380,000 years old, when the first atoms were forming and light was becoming free to travel through space for the first time. If the speed of light was different back then, if the fundamental constants had slightly different values, those differences would be frozen into the cosmic microwave background like fossils preserved in amber. But the cosmic microwave background is just one source of information about varying constants. The universe has provided us with many other natural laboratories for testing the constancy of physical laws, each with its own unique advantages and challenges. Gamma-ray bursts, those brilliant flashes of high-energy radiation that occasionally light up the cosmic sky, offer another window into the deep past. These events, which occur when massive stars collapse into black holes or when neutron stars collide, produce some of the most energetic photons in the universe. Dr. Floyd Stecker at NASA's Goddard Space Flight Center has been studying how these high-energy photons interact with the quantum vacuum as they travel through space. According to some theories, if fundamental constants are varying, this interaction might depend on the photon's energy in subtle ways. By comparing the arrival times of gamma-ray bursts at different energies, researchers can search for evidence that the speed of light might depend slightly on photon energy. Such energy-dependent propagation would be a smoking gun for varying constants, providing direct evidence that the fundamental structure of space-time is more complex than current theories suggest. The searches conducted so far have found no convincing evidence for such effects, but each null result helps constrain how much variation is possible while remaining consistent with observations. Science progresses as much through ruling out possibilities as through confirming them. Perhaps even more intriguingly, some theories predict that the effects of varying constants might only become apparent under the most extreme conditions. Near black holes, where gravity becomes so strong that space-time itself begins to behave in exotic ways, the fundamental constants might take on values significantly different from their terrestrial values. Dr. Dimitrios Saltis at the University of Arizona has been developing techniques to test this possibility using observations of matter falling into black holes. As gas spirals inward toward the event horizon, it heats up to billions of degrees and emits X-rays with characteristic spectral features that depend on the values of fundamental constants. By studying these X-ray spectra with sufficient precision, researchers might be able to detect whether fundamental constants behave differently in the extreme gravitational environments around black holes. Such measurements would provide unique insights into how gravity and quantum mechanics interact at the deepest levels of reality. The Event Horizon Telescope, which captured the first direct images of black holes, is opening new possibilities for such tests. By observing the behavior of matter and radiation in the immediate vicinity of black hole event horizons, astronomers can probe physics under conditions that cannot be replicated in any terrestrial laboratory. These observations are pushing our understanding of fundamental physics into entirely new regimes. The combination of intense gravity, extreme temperatures, and relativistic motion creates natural laboratories for testing whether the laws of physics remain constant under the most extreme conditions the universe can provide. Dr. Ferial Ozel at the University of Arizona has been at the forefront of interpreting Event Horizon Telescope observations in the context of fundamental physics. Her work shows how the detailed structure of black hole images depends sensitively on the values of fundamental constants, opening new avenues for testing their constancy. But perhaps the most profound implications of varying constants go beyond physics itself, into questions about the nature of scientific knowledge and the relationship between mind and cosmos. If the laws of physics themselves can evolve, what does that tell us about the permanence of scientific truth? Dr. Lee Smolin at the Perimeter Institute has argued that varying constants point toward a more evolutionary view of physical law. Rather than eternal, mathematical truths imposed on the universe from some transcendent realm, the laws of physics might be more like biological traits that emerge and evolve within the cosmic system itself. This perspective suggests that what we call scientific laws might be better understood as patterns that have emerged during the universe's long history of self-organization. Like the complex behaviors that emerge in biological ecosystems or social systems, physical laws might be the result of cosmic evolution rather than its fundamental cause. Such ideas challenge some of our deepest assumptions about the nature of scientific explanation. We're accustomed to thinking of physical laws as providing the foundation for everything else that happens in the universe. But perhaps the relationship is more circular, with laws and phenomena co-evolving together in an ongoing cosmic dance. This doesn't diminish the value or reliability of scientific knowledge. Even if physical laws are evolving, they're doing so on timescales so vast that they remain effectively constant for all practical purposes. The physics we use to build bridges and launch spacecraft will continue to work perfectly well, regardless of whether fundamental constants are drifting by a few parts per billion over cosmic time. But it does suggest a more humble and dynamic view of our place in the cosmic story. We're not just observers of an eternal, unchanging universe, but participants in an ongoing process of cosmic becoming. Our scientific investigations are themselves part of the universe's ongoing effort to understand itself. Dr. Sarah Walker at Arizona State University has been exploring these philosophical implications of varying constants in the context of astrobiology and the search for life elsewhere in the universe. Her work suggests that if physical constants can vary, then different regions of space might be more or less conducive to the emergence of complexity and life. This raises fascinating questions about cosmic evolution and the distribution of life throughout the universe. Are we living in a particularly favorable cosmic neighborhood, where the constants happen to have values conducive to biological complexity? Or might life be a driving force that actually influences the evolution of physical constants over cosmic time? These are speculative ideas, far beyond what current observations can confirm or deny. but they illustrate how the question of varying constants connects to some of the deepest mysteries about existence itself. Why does the universe exist? Why does it have the particular structure and laws that we observe? Are consciousness and physical reality somehow fundamentally intertwined? As you drift deeper towards sleep, let these questions wash over you like gentle waves on a cosmic shore. The universe we inhabit is far stranger and more wonderful than our ancestors could have imagined. Stars are nuclear furnaces. Space and time are unified in a four-dimensional fabric. Matter and energy are interchangeable. And now perhaps even the most fundamental constants of physics are participants in an ongoing story of cosmic evolution. Tonight, as ancient starlight streams through your window, remember that you're witnessing the latest chapter in this cosmic story. The photons reaching your eyes began their journey in distant stars, traveled through a universe where fundamental constants might have had slightly different values, and arrived here to participate in the miracle of conscious observation. Each blink of your eyes, each breath you take, each thought that drifts through your mind is made possible by the precise values of fundamental constants that have been slowly evolving since the cosmic dawn. The speed of light, the strength of gravity, the masses of particles, all apparently fine-tuned to allow for the emergence of complexity, beauty, and awareness. Whether these constants are truly eternal, or whether they're slowly drifting toward new values remains an open question. The evidence is subtle, the measurements challenging, the implications profound. But the very fact that we can probe such deep questions speaks to something remarkable about the universe's capacity for self-reflection. We are the cosmos becoming conscious of itself, using instruments and theories and patient observation to explore its own deepest nature. Through our research into varying constants, the universe is slowly discovering whether its most fundamental properties are as unchanging as they appear, or whether they too are part of the grand adventure of cosmic evolution. Rest now in the knowledge that this cosmic investigation continues while you sleep. Somewhere in the data streams from distant telescopes, in the precise ticking of atomic clocks, in the subtle patterns of ancient light, the universe is slowly revealing its secrets to those patient enough to listen. And tomorrow, when you wake to a world where light still races through space at its familiar speed, remember that you've touched one of the deepest mysteries in all of science. The question of whether the speed of light is changing over time remains beautifully, tantalizingly unresolved. But in asking this question, in pursuing it with such dedication and precision, we're participating in something profound. We're helping the universe understand itself, one careful measurement at a time. And perhaps that understanding, that cosmic self-awareness, is itself part of why the fundamental constants have the values they do. Sweet dreams, fellow explorers in this magnificent cosmos, where even the speed of light might be dancing to rhythms we're only just beginning to hear. But what does all of this mean for you, resting here in this quiet moment? What does it mean to live in a universe where even the most fundamental constants might be participants in an ancient story of change? Perhaps it means that nothing, absolutely nothing, is truly separate from the cosmic flow of becoming. The atoms in your body were forged in stellar furnaces billions of years ago, when the speed of light might have been ever so slightly different. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every organic molecule within you, all emerged from nuclear reactions governed by physical constants that may have been slowly drifting even then. Dr. Katie Fries at the University of Texas has spent years contemplating these connections between cosmic evolution and biological existence. Her work suggests that if fundamental constants were significantly different, the universe might never have developed the complex chemistry necessary for life. Stars might burn too quickly or too slowly. Heavy elements might never form. Planets might never coalesce from cosmic dust. Yet here we are, conscious beings capable of measuring the speed of light to extraordinary precision, of detecting variations smaller than 1 part in a billion, of peering back through cosmic time to study the universe when it was young. Our very existence seems to require that the fundamental constants have remained stable enough for long enough to allow complexity to emerge and flourish. This realization brings a sense of cosmic gratitude, doesn't it? Not just for our individual lives, but for the entire magnificent chain of cosmic evolution that made consciousness possible. The slow drift of physical constants, if it's real, has somehow managed to remain gentle enough that stars could form, planets could cool, chemistry could complexify, and awareness could emerge. Tonight, as you lie there breathing slowly, you're participating in this ongoing cosmic experiment. Your heartbeat marks time according to rhythms established by fundamental constants. Your neurons fire using electromagnetic forces that depend on the speed of light. Your very thoughts emerge from quantum processes governed by the same physical laws that determine how photons race across intergalactic space. And if those laws are indeed slowly changing, then you're witnessing a moment of transition in cosmic history. Future beings, if they exist billions of years from now, might inhabit a universe where the speed of light has drifted to values we can barely imagine. They might look back at our epoch the way we look back at the cosmic microwave background, seeing it as a relic from a time when the universe was fundamentally different. Dr. Frank Wilczek at MIT has speculated about such distant futures, where the gradual evolution of physical constants might open entirely new chapters in cosmic history. Perhaps forms of matter and energy that are impossible today will become stable in the far future. Perhaps new types of complexity, new forms of organization, new varieties of consciousness will emerge as the universe continues its patient journey of self-discovery. But these are dreams of times so distant that the sun will have long since exhausted its fuel, our galaxy will have merged with others, and the very concept of planets and biology might seem quaint to whatever forms of awareness inherit the cosmos. For now, we live in an epoch where the constants are stable enough for stars to shine steadily, for planets to maintain stable orbits, for life to persist across geological ages. This stability in the midst of change might be the universe's greatest gift to consciousness. Like a calm harbor that protects ships from storms while still allowing them to venture into deeper waters, the slowly varying constants provide just enough stability for complexity to flourish, while keeping just enough flexibility for evolution to continue. As your breathing deepens and your thoughts grow quieter, let yourself feel held by this cosmic balance. You're not just lying in a bed on a planet orbiting a star. You're resting within a universe that has somehow managed to fine-tune itself for the emergence of beauty, complexity, and awareness. The speed of light, racing through space at nearly 300 million meters per second, might be carrying messages not just from distant galaxies, but from distant epochs when the universe itself was learning how to create the conditions for minds like yours to emerge. Every photon that reaches your eyes is a messenger from cosmic history, carrying information about how physical reality has evolved over billions of years. And tomorrow, when you wake to sunlight streaming through your window, you'll be greeting photons that began their journey in the sun's core just 8 minutes ago. Those photons race through space at the speed of light, a speed that might be just the tiniest fraction different from what it was when the sun first began to shine 5 billion years ago. The difference, if it exists at all, would be imperceptible, but it would be real. Part of the ongoing story of how the universe continues to write itself into new forms of existence. You're not just observing this cosmic story, you're part of it, a conscious moment in the universe's long journey of becoming. Rest now in that knowledge. Let the gentle possibility of changing constants remind you that even in a cosmos of unimaginable vastness and age, change happens slowly enough for beauty to emerge, for love to grow, for consciousness to contemplate its own existence. The speed of light, that cosmic constant we've trusted for so long, continues its patient journey through space and time. Whether it's changing or remaining perfectly constant, it carries the light that makes vision possible, the electromagnetic radiation that powers our technology, the quantum fields that govern the very atoms of which we're made. In the end, perhaps the most profound truth isn't whether the speed of light is changing, but that we live in a universe capable of supporting minds curious enough to ask such questions. We exist in a cosmic moment where physical constants are stable enough for science to flourish, where consciousness can emerge and begin to understand its own foundations. Sweet dreams, fellow travelers in this magnificent cosmos, where even the deepest laws of physics might be dancing to rhythms older than stars, gentler than time, and more patient than the expansion of space itself. And as you drift into sleep, remember that tomorrow will bring new light, new measurements, new data from the cosmic deep. The ancient question of whether fundamental constants truly remain constant continues to unfold, one careful observation at a time, in laboratories and observatories around the world. The universe keeps its secrets well, but it does eventually share them with those who ask the right questions and wait patiently for answers. Whether the speed of light is changing over cosmic time remains beautifully, mysteriously unresolved. But in pursuing this question with such dedication and precision, we're participating in the universe's ongoing effort to understand itself. And perhaps that cosmic self-awareness, that capacity for wonder and discovery, is itself the most constant thing of all. But perhaps the most beautiful truth is this: whether the speed of light changes or remains forever constant, you are here now to witness its journey. Right at this moment, photons are streaming through space, carrying messages from the cosmic past, racing at that familiar speed we've measured so precisely, yet which might be whispering secrets about time itself. Think of it this way: every breath you take unfolds in a universe where physical constants have remained stable enough for your lungs to work, for oxygen to bind with hemoglobin, for your brain to process these very thoughts. If the fundamental constants were wildly different, if they changed rapidly or dramatically, none of this quiet contemplation would be possible. Dr. Paul Steinhardt at Princeton University often reflects on this cosmic gift of stability within change. His work suggests that the universe seems to have found a remarkable balance, allowing for evolution and transformation on the grandest scales, while maintaining enough consistency for complex structures like stars, planets, and living beings to persist across billions of years. Even if the speed of light is drifting slowly toward new values, even if the fundamental constants are participating in an ancient dance of cosmic becoming, the changes are so gentle that they form a stable foundation for everything we know and cherish. Your heartbeat, your memories, your capacity for wonder, all rest upon physical laws that have remained essentially unchanged throughout the entire history of life on Earth. This is perhaps the deepest message hidden within the search for varying constants. Not that the universe is chaotic or unpredictable, but that it has somehow learned to balance permanence with possibility, stability with transformation, like a vast symphony that maintains its essential melody while allowing for subtle variations and improvisations. The cosmos seems to know how to preserve what matters while still leaving room for growth and discovery. As you rest here in this gentle space between waking and dreaming, let yourself feel grateful for this cosmic balance. The speed of light, whether constant or slowly changing, continues to weave together the fabric of space and time that makes your existence possible. It carries the warmth of distant stars to your skin, the information that creates the images in your eyes, the electromagnetic forces that hold your very atoms together. Tonight, while you sleep, that ancient light will continue its patient journey across the universe. Some photons will complete voyages that began billions of years ago, finally reaching Earth after crossing unimaginable distances through space that might have slowly, gently changed around them. Other photons will begin new journeys from distant stars, carrying fresh messages toward futures we can barely imagine. And somewhere, in laboratories around the world, atomic clocks will continue their precise ticking, measuring time with accuracy beyond human comprehension. Radio telescopes will gather faint signals from the cosmic deep. Researchers will analyze data, refine theories, and slowly piece together the story of how physical reality has evolved since the beginning of time. The question of whether the speed of light is changing remains beautifully open, suspended between certainty and mystery, like a star balanced between gravity and nuclear fire. But in asking this question, in pursuing it with such dedication and wonder, we participate in something profound. We become the universe contemplating itself, consciousness turned toward the deepest puzzles of existence. Rest now, knowing that you are part of this ancient conversation between mind and cosmos. Whether the speed of light is eternal or evolving, it continues to illuminate the world around you, to make vision possible, to connect distant regions of space and time in ways that allow beauty and understanding to emerge. Sweet dreams, fellow traveler, in this magnificent universe where even the most fundamental constants might be learning new steps in the eternal dance of becoming. Tomorrow will bring new light, new questions, and new opportunities to wonder at the deep mysteries that surround us. The speed of light races on through space and time, carrying its secrets patiently toward whatever revelations await. And you, consciousness briefly awakened in the cosmic dark, rest now in the gentle certainty that some questions are more beautiful for remaining open, more profound for inviting continued exploration. Sleep well, knowing that the universe continues its patient work of self-discovery, one photon at a time, one careful measurement at a time, one moment of wonder at a time. And perhaps that's the most constant thing of all, this endless capacity for growth, for change, for the slow emergence of understanding from the beautiful darkness of the unknown.